inductance. So we know that a current carrying conductor, it will produce a magnetic field. Okay, but if you consider it in terms of the closed circuit, right, because whenever there is a current, it means that there will be some closed circuit, only then current can flow. So whatever magnetic field is produced, the field lines, they are passing through this circuit, right? The closed circuit is enclosing some flux lines. Okay, so let us say the flux passing through the circuit is phi. Now if you have n number of identical turns, okay, like in this case here, so we are winding a conductor this many times. Okay, then what is happening here, there is some flux being produced and it is being linked to each loop n times. If there are n number of turns, then n times the flux is being linked. Okay, so here we are going to define something called as the flux linkage. Okay, so if there are n number of turns, then the flux linkage is defined as flux linkage, we denote it as lambda. This is defined as n times the flux due to each turn. Okay, flux linking with each turn. Okay, so this is called as the flux linkage. Now this flux linkage, it is proportional to the current that is passing through the circuit. Okay, so the magnetic field lines here, it is going to be in this way. Okay, so if the current that is passing through this is I, then the flux linkage is going to be proportional to I. Lambda is proportional to I. Okay, so here you can get the constant of proportionality is L. This is nothing but the inductance that is associated with the coil. Okay, so this is nothing but the constant of proportionality. Okay, so this expression here is important. Now the physical significance of inductance, what does it convey? Okay, because if you take a resistor, then R is some constant of proportionality. What does it, in a physical sense, what it conveys? It conveys the opposition that is offered to the current flow, the flow of current, right? Similarly, inductance also has some physical significance. It is the ability to store magnetic energy. Okay, so L or inductance is the ability to store magnetic energy. So just like in the case of capacitor, what it did, more the capacitance, more charge can be stored. More charge stored means that there is more electrostatic energy. Okay, so just like capacitance is the ability to store electrostatic energy. So L we can write as, from the previous expression, this is the flux linkage divided by the current, or we can further write it as N phi by I. Okay, and the unit of the inductance is Henry. Unit is Henry. So in the case of a capacitor, we have seen the energy that is stored, the electrostatic energy is half CV square. Here the magnetic energy that is stored in the inductor, this is half Li square. Magnetic energy stored in inductor is half Li square. Lastly, we know that the inductance is a constant of proportionality, right? So just like resistance and capacitance, it depends on the geometrical configuration of the inductor. Okay, so let's take a core, okay, around which the coil is wound. So this is an inductor. Okay, so often it is air cooled, right? That means there is no core, there is only air. So here let us say the number of turns is n. Okay, the number of turns is n, and the area of cross section is A. This is area of cross section of the core, right? That is A, and the length of the coil, that is L, let us say. Okay, So from here we can get the inductance is equal to mu n square A by L. Okay, what is mu? Mu is the permeability of the material, where mu is permeability of the material around which the coil is wound. Okay. Now we will see what is self and mutual inductance. Okay. So what happens is, whenever there is a coil, okay, so we will take a coil like this. Whenever there is a coil, the current that is passing through it, let us say it is I1. Now the magnetic field will be produced here, right? Now this flux is linking this coil. Okay. So the flux is produced by the current in the same coil. Okay. So in this case, the inductance associated with it is called the self inductance. Okay. But let us take two different coils. So this is one coil, okay, and this is the second coil. This is coil 1, coil 2. Okay. Now because of the current through this first coil, there will be some flux that is produced, okay, and the flux is linking with the turns of the same coil. Okay. But it will also produce magnetic field which is linking the second coil. Okay. So that means there is flux linkage of coil 2 because of the magnetic field produced by current 1, magnetic field produced in some other coil. Okay. So here the whatever inductance is associated, right, there is still flux linkage. So this flux linkage divided by this current is now going to give you the mutual inductance. Okay. So that is the difference. Self inductance is the flux linkage due to the current in itself. Mutual inductance is because of the inductance associated with flux linkage produced by current in some other coil. So here you can write down, when flux linkages are produced by current in the inductor itself. Then the associated inductance is self inductance. But if there are two coils as shown in the figure, then what is going to happen? There is a magnetic interaction, right? The magnetic flux of one coil is being linked to the other coil. Okay. Then there is a magnetic interaction between the two. So the flux produced due to one coil links the other coil as well. Okay. So the associated inductance is called the mutual inductance. So you have to understand one thing here, there is self inductance as well. Okay. So because of this magnetic field, there is flux linkage here. So there is a self inductance of coil 1 because of current I1. There is mutual inductance of coil 2 because of current I1. So here you will have two different mutual inductance. Okay. So M12, this is due to flux linkage of circuit 1, linkage of circuit 1 due to current in circuit 2. Okay, that means some current is flowing in coil 2, and because of that there is some flux linkage in circuit 1. So that inductance is M12, we represent as M12. Okay. And similarly you have M21, this is due to the flux linkage of, rather than circuit we will take coil. Okay. Coil 1 due to coil 2, right. Here this is because of coil 2 due to current in coil 1. Okay. So these both inductances, they are going to be equal. Okay, M12 is equal to M21, both are equal. So when the mutual inductances are also considered, then what will be the magnetic energy? Okay, total magnetic energy of the system is equal to Wm, this is half L1 I1 square, the energy due to the self inductance of coil 1, plus half L2 I2 square because of the self inductance of coil 2, okay, plus or minus M12 I1 I2. Now what is this positive and negative sign? When do we use a positive sign and when do we use a negative sign? Okay, so positive sign is used when the currents are such that the magnetic field will strengthen each other. Okay, so you will be able to understand this better if we take a transformer core like this. Okay, here there is one coil and here there is a second coil. Okay, now let us say the current that is flowing through this is I1. Okay, now if you apply the right hand rule here, then what will be the flux direction? The flux direction is going to be in this sense. Okay, now this is the, you can see this is the flux that is linking the second coil. Okay, now let us say here also some current is flowing, I2. Okay, so this current is like this. Okay, now if you apply the right hand rule, then again you are going to get a field in this direction, in the same direction as that which is produced by I1. Okay, so in this case the fields are strengthening each other. Okay, strengthening field directions. Now if you take another case, so we will take the same sense of windings. Okay, here also there is a coil 1 in the same sense. See, this is also winded in this way, this is also wound in this way. Okay, so next is second coil, this is also in the same way, but here we will take current I1 like this. So because of this we have the flux in this direction, right? Now here the current we will take in this direction, it is flowing out. Okay, so what will be the current direction here? It is going to be like this. Okay, now if you apply the right hand rule, then what will be the direction of the flux? Now there is going to be a flux which is opposite to that produced by I1. Okay, so here the fields are, they are differential in direction. Okay, they are opposite direction. Okay, so opposing field direction. Okay, in this case we use the positive sign and in this case we use the negative sign. Okay, so here you can write positive sign if fields are strengthening each other. Okay, and negative sign if fields are opposing each other. Okay, so depending on the direction of the field, you are going to take the appropriate sign. Okay.